there are some other things that the planetary model did not satisfy, okay? So for example, why? Why is there set quanta of energy, okay? Why do electrons only reside at certain energy levels? Why can't they just be at any one they want to be at, okay? Why is that? The planetary model doesn't really tell us that, okay? We also were getting some new research. We were seeing some really weird behaviors of electrons when we were testing them in the late 1800s, early 1900s. Some things that were very, very different than we would expect out of a tiny little particle, okay? So we've always viewed electrons as these tiny little bits of matter, okay? And they must be moving like a little tiny little like speck of sand through our universe. Well, we were finding out from data, we meaning not me, I mean it's people who are way smarter than me, they're finding out that, wait a minute, the electrons aren't always moving and traveling and acting the way you would think like a tiny piece of matter would move, okay? As a result, we now have a better theory of what the electron really is, okay? And in fact, this is a theory that we've known since the early 1900s, but it's not one that gets taught very often unless you get into high school or higher level physics or chemistry, because it's really abstract, okay? Because it's really, really easy to visualize atoms and electrons as bits and pieces of little tiny spheres of matter. But when you tell somebody that the electron, this particle that we know exists, that we actually can map out its mass, is actually a wave of energy and not a particle at all, people go, whoa, no way. And that's what you're doing at home now. You're going, whoa, no way. But yeah, it's true. But then, to make things even worse, we say, but it's still a particle. And you're like, whoa, what do you mean? It's like, well, it's a wave of energy, and it's a particle. And you're like, okay, well, does it change? Like, sometimes it's this, and sometimes it's that. It's like, no, it's both, all the time. You're like, oh, well, that's not really helpful for me. Well, that's the weirdness of quantum mechanics. That's the weirdness of going into that quantum model, is things aren't like the macroscopic world where, you take an apple, throw an apple. It's going to fly the way you think an apple is going to fly. Okay? It's not going to magically turn into a wave pattern and bend around things. Electrons can do these things, which is super cool. Now, because of that, okay, because of this dual nature of electrons, we now know that the model of our atom being orbiting particles is not the best model. We have a better model for it, okay? So we have to have a better grasp of this dual nature of electrons. So for us to do that, first of all, just accept it with me for now, that electrons behave like particles and like waves. They do both, okay? And it's no different than, let's say you're a two-sport athlete. He's like, oh yeah, what do you do? I play hockey. Okay, and I'm a cross-country runner. It's like, what do you mean you can't be both? Like, yeah, I can actually, I can be both. Now, the difference is you don't do a cross-country race during a hockey game. That doesn't happen. Electrons can do both at the same time, which is why the quantum world is so weird to us, right? Here is our reason why, okay? So we have to have experimentation to show data to support this theory. We can't just say it exists and someone go, oh, I believe you, it's fine. You must be smarter than me, and you say electrons are waves. Cool, Mr. Dirksen, I'm with you. No, okay? We need to have some sort of empirical data to show it. The experiment that was run is called the double slit experiment. It's actually one of the most famous experiments in the atomic world because it's so simple, okay? And we're going to watch a little video on that next because the video does a much better job of going through it than I do. So here we go.
And here we are.
Oh, it's a cartoon too, which makes it way more fun.
The granddaddy of all quantum weirdness, the infamous double slit experiment. To understand this experiment, we first need to see how particles, or little balls of matter, act. If we randomly shoot a small object, say a marble, at the screen, we see a pattern on the back wall where they went through the slit and hit. Now, if we add a second slit, we would expect to see a second band duplicated to the right. Now, let's look at waves. The waves hit the slit and radiate out, striking the back wall with the most intensity directly in line with the slit. The line of brightness on the back screen shows that intensity. This is similar to the line the marbles make. But when we add the second slit, something different happens. If the top of one wave meets the bottom of another wave, they cancel each other out. So now there is an interference pattern on the back wall. Places where the two tops meet are the highest intensity, the bright lines, and where they cancel, there is nothing. So, when we throw things, that is, matter, through two slits, we get this, two bands of hits. And with waves, we get an interference pattern of many bands. Good so far. Now, let's go quantum. An electron is a tiny, tiny bit of matter, like a tiny marble. Let's fire a stream through one slit. It behaves just like the marble, a single band. So, if we shoot these tiny bits through two slits, we should get, like the marbles, two bands. What? An interference pattern. We fired electrons, tiny bits of matter through. But we get a pattern like waves, not like little marbles. How? How could pieces of matter create an interference pattern like a wave? It doesn't make sense. But physicists are clever. They thought, maybe those little balls are bouncing off each other and creating that pattern. So, they decide to shoot electrons through one at a time. There is no way they could interfere with each other. But after an hour of this, the same interference pattern is seen to emerge. The conclusion is inescapable. The single electron leaves as a particle, becomes a wave of potentials, goes through both slits, and interferes with itself to hit the wall like a particle. But mathematically, it's even stranger. It goes through both slits and it goes through neither. And it goes through just one and it goes through just the other. All of these possibilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through.
All right, so what we just saw there, if I back it up a little bit, this is where it gets a little confusing. Just gets confusing. It's a little bit small, but these things spinning in the air right here, those are actually different wave functions. So they're different equations that mathematically are true that could show the electron acting as a wave. Okay, they are different forms of the Schrodinger wave equation, which he's kind of famous for developing. So all of these possibilities have equal probability of happening for an electron acting as a wave. Okay, so we're now in the quantum world where we're no longer saying yes and no's. It's all about what's the probability of this happening. What is the likelihood of this happening? Is it mathematically possible for this happening? Well, yes, we have mathematical expressions, and I won't show you each one of these because you can't see them and they're confusing. But we have the ability to show mathematically that yes, electrons can move as waves, and there's all these different probabilities of how it's passing through these different slits.
Probabilities are in superposition with each other. But physicists were completely baffled by this. So they decided to peek and see which slit it actually goes through. They put a measuring device by one slit to see which one it went through and let it fly. But the quantum world is far more mysterious than they could have imagined. When they observed, the electron went back to behaving like a little marble. It produced a pattern of two bands, not an interference pattern of many. The very act of measuring or observing which slit it went through meant it only went through one, not both. the electron decided to act differently. As though it was aware it was being watched. And it was here that physicists stepped forever into the strange, never world of quantum events. What is matter? Marbles or waves? And waves of what? And what does an observer have to do with any of this?
All right, so it's okay if your brain hurts a little bit, because it should, because this is stuff that's very different unless you've heard it before or kind of read through it before on your own, okay? Now, I do want to clarify a couple of things when it comes to this and that observer. Now, they make the observer look like it's a nice little eyeball, just someone looking at it. But remember, we can't see atoms. We can't see electrons. So when you talk about observing what the electron does, there's only one way that we can observe electron behavior, and that is by giving it energy, okay? So if we want to observe what's going on, we either have to observe it from afar, meaning indirectly, then we can't tell exactly what it's doing, or we can observe it closely. But to do that, we have to give it energy. Well, as soon as you give it energy, it changes its behaviors, okay? It's no different than you guys, right? If you're hanging out with your group of friends, okay, in your basement, let's say, and mom or dad walks downstairs, your behavior never changes at all, right? In the presence of an adult or somebody else in your life. You act the exact same way you normally would, right? Absolutely. Of course not. I still change how I behave around my mom sometimes, and I'm 43 years old, okay? So that is very true of electrons. Now, electrons aren't like living things that make decisions, okay? But the analogy holds because the electron, when you give it energy, those wave functions, those probabilities, as soon as you change that mathematical relationship, when you add energy and you add a new variable in, now you've changed the parameters. So by adding energy in, you now change its behavior and you collapse the possibilities of it acting like a wave. So only the possibilities of it acting like a particle still exist. I know. That can be really, really hard to swallow in your brain. Don't worry about it, okay? So take homes from this is a couple of things. One, we have to accept the fact that electrons, these tiny bits of matter, behave both like a wave and like a piece of matter. We have to accept that they can do so simultaneously together. You may not completely grasp why or how. You have to appreciate that there's an experiment that can show this, that the data is the same all the time, every time we do this through the years. Nothing changes it, okay? You have to appreciate that there's actually a mathematical foundation that shows electrons can move as a wave through the Schrodinger wave equation, okay? And you need to appreciate that there's a certain level of uncertainty in this because this is all based off of probabilities, okay? Which leads us down this road of this guy named Heisenberg in the Heisenberg uncertainty principle, okay? But at the end of the day, if you can just accept the fact that electrons move as waves and particles, that's awesome, okay? Because that's going to lead us down the road of why do electrons not orbit, okay? And why do electrons not act like planets around an atom? And that's what we're heading towards, all right?